getting into the solution method for the structure reliability. Solution method for structure reliability. You know the equations to solve, but we really looking into the concept using two random variable space R and S, or sigma Y and sigma S. Then we really look at inside a story what's happening. Lots of class of problem fall into that category, or you can really converge into the two random variable problem as you know, preliminary study or the feasibility study. The problem to solve is PF or PR, it doesn't make any difference, which is as integration is going to be something like fx x dx less than equal to 0. In the compactness to express the equation to solve, this is it. Not more or not less. So that's what the equation said. You have to do it. But now the problem, so if I just put one more steps between, this is a probability such that, use the same notation, Gx is less than equal to 0 is equal to this. Nothing more, nothing less. But here, when we use, you remember we use M is equal to R minus S or sigma Y minus sigma S. It's the same thing. And this as a whole thing, you can say this is like Gx. X is the random, the variable. It's very similar expressions, but this is a two random, the variable situation. And X, whenever I write the capital letter, that's the random family of random variable. Or you can say here, this is equal to the xi. I is equal to 1, 2, all the way through the n. Okay. N different random variable. You can write this guy as maybe xi. In this case, it's only the 2. So this is about all, no more, no less. That's all you can tell. And here, here the gx has a particular name. I already talked a few times. This is called the performance function. Couple different names, the people using it, or limit state. This is sometimes called limit state function. Okay, and this is a PF. This is a probability density function, of course, for the X random variable. Up to two random variable we can cast into the 3D space. Then it is very nice. You can really visually see this nicely. X1, X2. In this case, it's X1, X2. You can cast into the any forms. How can I draw? This is a joint probability density function. Yeah. The volume, you can put that in. And so I'm pretty sure I make a color copy for you last Friday, Wednesday. Okay, this could be random variable, could fall into everything, not just R and S, and you can cast whatever the dimensions, material properties, all the loading, type of the loading, you can designate for different the random variable. You can assign as many random variable as you want. Who select? You select, because you are the designer. Yeah. Then question arises, if this is an n-dimensional random the variable, and this is n-dimensional, of course, if it's all correlated, what you have to do? You just walk out. You can't solve the problem. Nobody knows the degree of correlation among the random variable. So I feel God didn't create that mode, because he clearly said in the Bible, I love you very much. That's what he said in the Bible. I gave you only begotten Son. So I feel it's not totally independent, but when you assume the independent, mutually independent among the random variable, it's not bad at all. So another the exclusive sort of the assumption made and used is normally distributed. For multi-degrees of freedom, multi-dimensional situation in the random space, if it's mutually exclusive, first of all, mathematically, as I mentioned, for the two-parameter situation, very easy to solve. Even two random variable, and it's a normal distribution, normal probability model, so easy. But if I inject the log normal distribution, as you saw in the second exam problem, not that easy. Second exam problem. So you have to just leave as integration form. I can't proceed any further. But if you assume like both normal distribution is everything cast into the standard normal distribution mode, then you can solve it. This is like a first order method or second order method. That's what the beginning of the way to solve the problem. Otherwise, you have to do somehow the solve the numerically. You may not able to solve to get the solution, but you have to approach that. And another really approach, you could solve multi-dimensional integration. Then I can say you could try optimization technique. Optimization technique is, when you're getting into it, it's not just a linear programming technique you could use, but mostly falling into the non-linear programming, because variables are all non-linear. What I'm telling you before I really start is there is a class of the problem for the structure reliability problem, which is multi-dimensional, very tough to solve, but last some 20 years, there is a lot of good progress. But even if you approximate as a first approximation as mutually exclusive for each random variable, still the result is pretty good. That's what I'm telling you. So here, first order, the reliability method I'm really introducing here. First assumption I'll make it here is mutually exclusive, the random variable. And also the x, all the xi parameter, I'm going to assume the normal to get the sort of the closed form solution with additional approximation. But don't be disappointed. You could be the one to develop into the better solution scheme. About some 30, 40 years ago, when I graduate the university, all this stuff I'm talking from today is not developed. About 20 years ago, they start to develop into it, but still linear first order approximation, not even second order. Then second order step in and get the better solution. When I say first order, all the non-linearity is dropped out. Like using what series they're using? They're using Taylor series expansion. You know Taylor series expansion. And stop at the first order, which means two-term. Linear constant plus the linear term. That's what we are first order reliability methods. That's what I'm going to use it. I'm just giving you a little bit guideline what direction I'm heading in, okay? And try to get into the path that we exercised already in two-parameter situation, and we used the so-called reliability index. Did we? We use a reliability index like this, right? And this is a normal distribution. This is mu x, this is x, this is fx. And from here to here is beta sigma x, right? This beta is reliability index. From here to this point is point to the maximum peak for the probability density function. Of course, this case is the normal distribution. Once you somehow compute the beta, it's just a conceptual. From here, start from the origin to the maximum peak point, right? If that's the beta. Once you compute the beta, if this follows the normal distribution function, of course you throw that from the basic random variable to the normally distributed random variable. Then you can compute by this. This is what we did. No? We did? We did. So approach, I am taking same path, very similar path, but it's multidimensional. That generate lots of problems. But first we're gonna do first order, and all the majority problem, your term project and all that, I want you to use and program yourself the first order, the reliability method, then get the solutions, then we're gonna compare among your solutions, okay? So it's roughly what direction I'm going into it. And over here, I'm gonna say xi are, strictly speaking, this guy is mutually exclusive, which is same as saying statistically what? Independent each other. Independent each other. Okay? Independent each other, statistically independent. And there is no covariance. Covariance is all equal to 0, or correlation coefficient is equal to 0, or covariance is equal. There is no correlation among the If you do that, I'll just take still a little bit on the conceptual. Conceptual. using this, or I brought this, I gave you, did I give you this? Do you have, did you bring here? No? So I'm going to a little bit explain what's going on here. Then this explains your concept, physical concept, a little bit more clearly. If you look at what this surface is, this is F shown up here is fx, right? This case is has a two random variable. This is about all we can explain using 2. 3 is multidimensional. So in this case, is 2 random variables are x1 and x2. Something like R and S, or sigma y and sigma s. So this is a probability density surface fx. And this is, what do you think about this plane? This is a failure surface, right? That's really failure surface means if you look at the down here, there is gx1 comma gx2, right? So that's what the g is a limit state function, and when that is equal to 0, then that's the failure plane, right? So g x is equal to 0, that's the really failure, I would say, failure surface. But for the integration is less than equal to 0, and this is failure region. So I indicate there, right? And when gx is larger than 0, this is a safe region. In terms of probability of failure, I cut this by the failure plane, failure surface, but cut off the volume. You see, there will be a cut off volume, right? If you make a continuation of probability density function, that volume is the probability of failure. G less than equal to 0. Equal to 0 means including the surface, right? And if it's all this volume here shown here, this is probability of what? Volume is, if you do the computation for the volume, what do you call that? Probability of survivor, right? Right? Or it's called the reliability, right? All this volume is reliability. Of course, this reliability or probability of the survivor is has to be very large. Otherwise, your structure system is meaningless. So the majority probability of the failure, especially for structure system, has to be the failure rate, failure probability has to be very small, because the structure failure happens once, then that's the end of it, disaster. For the processing, all the equipments, electrical equipments has a different story because you can replace it. But structure, the cost of replacement is extremely costly. And it looks like this color area is lifted up from the baseline. Why? To look at the projection, of this volume project onto x1, x2 plane, to see the contour of a probability density model. You got it? To see the contour. This is it's a contour of the joint probability density function. So in this case, it's a 2D, so joint, meaning of the joint makes sense. But if it's a 3 or 4 or 5 dimensional, still you could possibly draw the contour. You can get down on the projections. Okay, so this is a contour line, has a meaning into it, because we're going to transform all this in the complex, the physical space into the other space. I could say the author, developer happened to be the Rosenblatt, so I could say Rosenblatt space, or normal probability space. There, everything, all the contour is not like this. This is center. This is not the circle. Could be any depend on the probability model of X. It could be some shape it could generate. But if it's a standard normal density function, when we transform into, we did, right? If X variables are normal, when we transform into the normal space for 2D situation, then if its original is normal, and even if normal variable, if you add it together, result is a normal. And when you transform into standard normal space, of course there's a normal, but everything is a symmetry. If I just cut it like this, if I look down here, this projection onto the x1, x2 space gonna be circle. You agree that? Circle. This is gonna be different contour, circle. This is gonna be a circle. So in the normal, standard normal space, all the contour will be, let's call the U space, U1, U2 space, is going to be nice circle. You buy that? That's beautiful. And this guy is centered at the origin. You can tell already. Very easy, simpleness, easiness. Integration, very nice, but not that easy because it's multi-dimensional. But that's what we are heading into, that direction. And what's this line along here? That's a G is equal to 0 in terms of the cut of a probability density function. You have a phase there. Surface, failure, surface. Got it? This is what I want to show nicely. And this is identical to this, x1, x2. I'm not good drawer, you call, so this is a better way I feel to explain. This is a projection of the failure surface G is equal to X. This region is X is less than equal to 0. If you exclude failure surface, it's going to be simply X is less than 0. In this region is greater than 0. All this different color, the line is a contour of probability density function. It explains well, I hope. And this is just a basic conceptual type of the integration we have to have for the multi-dimensional situation. And to approximation, we're going to use it. One method is FORM, another method is SORM. Two methods we're going to look at it as an approximation of approximation. FORM, first order, the reliability method. SORM, second order, the reliability method. That's what we're going to do. And the reading material which I provided to you covers this area, as I mentioned by XDO. It has, I give you the file, which I got it from the Professor Du, not published yet, but it's very good. It's very nice to understand. You can, when you read, it's very nice material that you can just understand very well, easily. But first material, it's all part of his book that he's writing already a few years. And first one is the material is something like this, right? Structure, reliability method, then SORM, FORM. That's the chapter 7 of his book. And as I read, very nice material to read. After that, he wrote, I think it's recently, he and two of his colleagues, three people, they wrote together MPP-based method. It's both are equivalent. But MPP is a little bit more mathematical, but I can say it's identical. But you could say why they wrote the same material twice. First one is by Du himself, and he gave a lot of thought to explain. And 2 is kind of a compact type. And the equation set is almost identical, but slightly different. But I want you to read first one is mandatory, you must read. Then second one, you will have plenty of time in the rest of the course. You should first read the first one, then Second one will not take much time to finish up the reading. They use a slightly different notation. I want you to read. It has examples. We're going to go through the first set, and I'm going to put the part of the second set into the first set in my lecture. Then you will hear the combined situation. And the first order, second the order use. So I said this is you have to read, and subsequently you will read that. Then I'll give you combined content in my lecture. So whole idea is the approximation. This is using all the approximation to solve nothing but PF. This is destination to compute the PF. Whether this is a processing reliability or structure reliability, your destination is to compute the PF for analysis. But for the design, PF is design PF is already set. Then you have to fit all your random variable to fit into the given or design probability of the failure or reliability. So for the simple, L is given, but you could have a cross-section. For the analysis, cross-section is given, right? Then you have to analyze it, and check it whether this beam would be survive or not based on the loading. Loading is given. Loading is given. But for the design concept is different. Design is different. What is given? Section is given? Yes, sir. Yes, sir. Not yes, sir. Yes, sir is, I like it. I love yes, sir. Yes, sir과 science. Yes, sir is art. Ali, you know? So section, for the design section is not given. You know, you can have a rectangle, you can have a circle, you can have a tube, you can have box girders, whatsoever. You can have a dead shape, any shape, right? That's up to you. What is given? Loading is given, right? You don't generate the environment yourself. Structure, offshore structure, you don't generate your own environment. Whatever given the environment. If it's a flooded whole city in Bangkok, you have to take it as is. You can't change the environment. That's the given. Then you have to determine this, but another possible other parameter would be what? Material. Right? You can change the material. I'm going to use very cheap material. What would be it? Maybe concrete, cheap? Maybe all the apartments is thick concrete, maybe cheap. Aluminum, cheaper than steel. So I would rather use aluminum for lawnmower shaft? You're going to use aluminum for lawnmower shaft for design? Why not? I mentioned to you before. Why not? Yes, sir, you're not going to use aluminum material for lawnmower shaft. Is very important, right? There is no endurance limit. There is no yield. So it's a sidetrack, but it's a very nice conceptual. That's it. There is no such a thing. No yield. It's just a degrading and finishes up. For any fatigue-sensitive material, you're not going to use it. So anyway, the sidetrack as approximation, use approximation, you compute the failure probability. For approximation, Taylor expansion theory. Series. You use the first order reliability method. You use the first two terms. First two terms. Whatever the equation comes in, like a G equation, performance equation. Performance. Only two terms. The constant term plus first order term. This is something like a G for the given point, which is called the expansion point. You remember all the Taylor series, right? Don't say no. Taylor series, this is called expansion point. You can use, rather than this guy, I can use x dot. And this guy is, second term is like a gradient of g at u dot, right? Or g, in this case, I use gx times x minus. This expansion point built around the given point. That's a first order approximation for g function, performance function, or limit state function. That's what you do, no more, no less. And for the second order reliability method, Arlene, what do you use? Using Taylor series, you add one more term, right? You have one more term, second order term, for better approximation. But a lot of class of the problem, this much two term is enough. For some class of the problem, you need the third term. That's what usually happens. For the submarine design is like a tube type, long length tube type configuration it has. The solution method, all the days we had in the US was so-called, you don't have to know detail, just example, so-called the DAA algorithm. That's DAA1, first order approximation, two terms. That's good enough to give a very, very good solution for the behavior of submarine. So use no reason to use additional term, which takes lots of more computational time. But when you have a compact structure, like a robot exploration type of the vehicle, first two term not enough. You have to bring the third term, that's a must. Third term, without the third term, actual physical behavior is totally different. Well, not totally, quite different from the behavior from the numerical result, are quite different from physical behavior, vice versa. So the first order and the second order, that's what we do. And to complete the conceptual thinking and idea, there are two different steps I want to give you. Two-step approach. Two-step. Two steps. Two steps to compute the probability of the failure is multiple because G is less than equal to 0. Each integration is associated with what? Each random variable, right? So here is, I can say PF1, PF2, up to, should I use a PF1 for a time being? Let's do that for a time being. But well, eventually this is independent, this is independent, this is all independent. Another area you have to consider is failure surface, because that's the really, right at the failure surface, integration stops. How to associate with the PF on that. That's what we have to work on. Rather than keep writing equation after equation, I want to do a little bit conceptual, get some conceptual idea, feel. Before you go out date, you've got to have a feel on your 남친 or 여친. Arlene, you know what's a 여친, 남친? 여친 is a girlfriend. 남친 is a boyfriend, right? Right? You have to have a feel. This is what I'm giving you, the feel a little bit. Then next, you have to go right into start to date. Right? You have to date how, otherwise all the days the parents, two different sets of parents introduce, okay, here is your partner, 남친, 여친, okay, marry. No, not nowadays. You have to go out date. What that means, we have to explore each step to getting into detail. Then after that, what you gonna do? Solve a few example problem. Then you have to program, right? Like a MATLAB program. Then get the real feel. Sometimes you're stuck, of course. During your research program, if you're never stuck, something wrong. Sometimes you will end up to solve the problem, spend month after month after month. Then you discover, gosh, that's the mistake, error. It happened, but that was so simple. But you spend 3 months already. But that's not the waste of time. So up to here, the direction, you saw it from Wednesday. We're going to attack each segment at the time. Then we're going to taste the detail. Okay? All right, so you got the material, and you can start reading, and we'll move on. And around mid-November, after solve one or two problem, then I want you to really set up your own the term project, then generate the program, get the results out, and maybe sensitivity studies and all that. I'll make out the project descriptions. Okay? Okay, I'll see you Wednesday.